All right, so we're going to start this video with E2 reactions. This is a one-step mechanism to form an alkene. And note that the starting material is a tertiary alkyl halide. So E2 and SN2 are completely different, and you should not relate them other than that they both depend, that both of these types of reactions, the only thing they have in common is that both the nucleophile and the electrophile reactant affect the rate. The type of reactant, in terms of the alkyl halide, there is no relationship between SN1 and E2 in terms of the type of reactant that undergoes the reaction mechanism. So in the first step, the nucleophile bonds, I'm sorry, that's not correct. I don't know where my brain went for a second. In the first step, what's going to happen is that a proton will be taken, and I'll do it from the same carbon that they're showing here, this one. So if we redraw it, we can draw CH2, CBr, CH3, CH3, and hydroxide ion. So the nucleophile comes and takes the proton. The bonding electrons for carbon to hydrogen fall to form the pi bond, and the halogen gets kicked off like a boot kick with its electrons, and that gives us as a final product our alkene and water, because the hydroxide gains a proton, and a bromide ion. So here we have the mechanism as shown by the book: hydroxide ion taking a proton, the bonding electrons from carbon to hydrogen forming a pi bond, and the halogen getting kicked off. This all occurs simultaneously. This gives us the alkene, water, and bromide. Now this can be significant on when we have a chiral carbon, because the hydrogen will always that is removed for an E2 mechanism must always be anti to the halogen that is kicked off. And so, for example, if we have a substituted halogen ring, and in a ring the hydrogen and the bromine that are kicked off must always be axial. For an E2 mechanism. So the H and the Br lost in a ring must be axial. And so, for example, if you're asked to do an E2 elimination of a ring that has the halogen atom in an equatorial position, you have to do a ring flip to find the correct product, because they have to be axial when they're eliminated. So then this hydrogen is removed by the base. It kicks off the bromine and forms a pi bond here. And that results in these two methyl groups that are on the pi bond will end up being cis after the pi bond forms, because we always have a cis pi bond. So showing the mechanism, the hydrogen is removed, we have the pi bond formed, and this gives us this final product. But also, there's another hydrogen that is axial to the bromine, and that is this one shown here. So is the pi bond going to form between these two carbons or these two carbons? And the answer is that the major product is going to be the more substituted pi bond. And so you have to pick and choose what your major product is going to be and what's going to result in the most stable product. Remember, the most thermodynamically favorable product, which will be the most substituted pi bond, will be the major product. Okay, so here's another example drawing it as a ring with hatches and wedges. You can still show the reaction. In this case, when the two methyl groups are cis, then if you draw the cyclohexane ring, what you see is that the hydrogen that on the position here, this hydrogen will never be eliminated to give the alkene because they'll never be anti. Okay, so they have to, both the hydrogen and the bromine that are lost have to be axial and they have to be anti to each other. Okay, but for this carbon, when bromine is axial, the hydrogen is equatorial. So this hydrogen cannot be eliminated to give a pi bond here. The only hydrogen that can be removed now with this other ring structure to give that is anti and axial to the bromide is this hydrogen here. And so then the final product, the only possible final product, is the product where we have a pi bond here. So this structure removal of this hydrogen, they're in the same direction, they're both on the bottom, so they're not trans to each other, then we can't remove that hydrogen. Okay. Whew. The halogen comes off the alpha carbon of the carbon that is alpha to the halide carbon. So terminology that they're going to use for our alkyl halides, they're going to call the alpha carbon the carbon bonded to the halogen, and the beta carbon the carbon that is adjacent to the alpha carbon. Okay, so the halogen, by their definition, is always going to be removed from the alpha carbon, and the hydrogen will always be removed from the beta carbon. So base removing the proton, same mechanism, the sigma electrons of carbon and hydrogen forming a pi bond, and the halogen leaving. E2 reactions are always regioselective when it will create an asymmetric bonds. So if our alkyl halide can result in either a monosubstituted alkene or a disubstituted alkene, the regioselectivity comes from that it preferentially makes the more substituted alkene. So that's regioselective because it selectively makes the more substituted alkene. So showing we have 2 bromobutane and there are 2 beta carbons. Both have hydrogens that can be removed. We make 2 products, 2 butene and 1 butene, and 2-butene is made at 80% mixture of E and Z, and 1-butene is made at 20%. And the major product is always the most stable alkene. So of the 80% that is 2-butene, more than half of that will be the trans alkene. So maybe, and I don't know how much, but greater than 40% will be the trans alkene. Or E. Okay, the most stable alkene is generally obtained by removing a hydrogen from the beta carbon that is bonded to the fewest hydrogens. So we can still use primary and secondary to refer to our beta carbons. So one of the beta carbons is primary and the other beta carbon is secondary. We are always going to remove a hydrogen from the beta carbon that has the fewest hydrogens, which is going to be the beta carbon that is the most substituted. So if you label your beta carbons by their substitution, primary or secondary, then you'll readily be able to choose which carbon the hydrogen will eliminate from. Here's the demonstration. 2-bromobutane with methoxide. Notice that the 1-butene is formed more slowly and has a higher energy final product, and the 2-bromobutane has a lower energy reaction transition state and is the lower energy final product. So the more stable alkene is the major product in the transition state that leads to the formation. One reason that it forms more quickly, and the second reason that it is a lower energy. We have an alkene-like transition state when this occurs. So the transition state is partial bonds at each position where bonds are going to form or break. So the bond to carbon and bromine is breaking, the pi bond is forming, the bond to carbon and hydrogen is breaking, and the bond between the base and the hydrogen is forming. This is the transition state leading to 2-butene, and this is more stable. It would give the more stable alkene, and then the transition state leading to 1-butene is less stable, having a less stable partial pi bond. All right, more E2 reactions to look at. We have this tertiary carbon that's a halide, and we have 3 beta carbons. So let's highlight our beta carbons. Whoops. Tertiary alkyl halide overall. And we can label our beta carbons as these 2 methyl groups are primary. And then the internal beta carbon that's not at the last carbon on the chain is secondary. Erg. Okay, so that's this carbon. And so I would expect removal of a proton from the secondary carbon to give the major product. And in fact, that is what you see. The secondary carbon is the carbon where the hydrogen was removed from to give us the major product at 70%. And then either one of the methyl groups loses proton, we get the minor product at 30%. The example below, we have I won't like red. 2 beta carbons, one is secondary and one is primary. And so it's predicted that the proton that is eliminated will come from the secondary carbon to give the major product. And that would produce 2-pentene, and it is the major product at 67%. And note that that is a mixture of the E and the Z isomer. And then removal of a proton from the primary carbon gives the minor product, 1-pentene. So very often when you're asked for the product of an E2 reaction, in a multiple choice question, they very often ask either what is the major product or what is the minor product. And occasionally they ask you to draw all possible products. Zaitsev's rule helps us to determine the major product of a reaction. Zaitsev's rule says that we will make the more substituted product as the major product, but there are limitations to this rule. One of the things that can limit the use of Zaitsev's rule, which is when we choose the more substituted product as the major product, I'm going to write Zaitsev's rule over here. So Zaitsev's product is the more substituted product. Substituted alkene product. So whichever gives the more substituted pi bond is going to be the major product, whether the more substituted pi bond is tetra, tri, or di, or mono substituted alkene. That's Zaitsev's rule, that we would get the more substituted alkene product. But there are limitations to this rule, and that is because you have to choose. Zaitsev's is referring only to more substituted pi bond, but the more substituted pi bond is not necessarily the more stable product. And that's where Zaitsev's rule fails. When the more substituted pi bond is not the more stable product, Zaitsev's rule will not apply. So you still have to figure out what both products are. So in the case, the major product for the first reaction that we're showing is a conjugated diene, and the new pi bond is only di-substituted, but it's conjugated. And we have delocalization energy because it's conjugated. Now, on the other, on the minor product, the new pi bond is tri-substituted, but it's an isolated pi bond that does not have delocalization energy. So in this case, you can see that Zaitsev's rule didn't apply because the more substituted pi bond was not the more stable final product. So if you have a product that will be conjugated, then the more stable product is the product which has conjugated pi bonds, not necessarily the one that has a more substituted pi bond. Another example is the benzene ring. So we have a benzene ring with an alkyl halide at the 2 carbons away from the ring. And so the major product is again going to be the product that gives us delocalized electrons or conjugated pi bonds. So a conjugated pi bond is always going to be more stable than a more substituted pi bond. So the major product ends up being the one with conjugated pi bonds, and the minor product is the more substituted tri-substituted pi bond. So we get a di-substituted new bond and a tri-substituted new bond, but di-substituted and conjugated is better than tri-substituted. So then in this case, if there is conjugation, the more substituted pi bond, why isn't that laser pointer working? Okay, the more substituted alkene is not the more stable alkene. Further limitations of the Zaitsev's rule occur when we have a bulky base. If you have a bulky base due to steric hindrance, the less stable final product will be the major product. So a bulky base selectively removes hydrogens from the less substituted carbon. So it will first remove hydrogen from primary, then secondary, then tertiary. Okay, so because the alkyl halide is tertiary and the bulky base is tertiary, we have to pick, the beta carbon that is the least sterically hindered to remove protons from, and that is going to be the less substituted carbon. So this bulky base will preferentially remove hydrogens from the more accessible methyl groups than from the less accessible secondary carbon that is in the middle of the molecule. And so the major product then is the product that comes from removing a proton from the less substituted carbon. And we can look at steric properties and the rate of reaction and the ratio of more stable to less stable for different bulky bases. So looking at base size, we have ethoxide, which is relatively small. The basic oxygen is bonded to a primary carbon, and that gives us 79%, the more stable alkene. When we move to the basic oxygen being bonded to a tertiary carbon, then the major product is the less stable alkene. And as the tertiary carbon gets bigger alkyl groups and becomes more sterically hindering to the oxygen, then we increase the amount of less stable product that is made. So the bigger the bulky base, the more of the less stable product is made. Okay. Alkyl fluorides will form the less stable alkene, and so they are unique. We know that fluorine is a poor leaving group, and we don't usually talk about using fluorine as a leaving group. But if fluorine is the leaving group, then the major product will be the less stable alkene, and we'll go through why that occurs. But the most important thing to realize is that the 1-pentene is the major product. Now let's look at some of the reasons why. The transition state, when we have fluoride, is similar to a carbanion transition state. And part of the reason that it is because that fluorine is very electronegative. And in a carbanion transition state, the less substituted carbon having a negative charge is the most stable position for the negative charge. So carbanions are going to be covered in chapter 11, metals. With the negative charge, more stable. So carbanions are the opposite of cations. A positive charge is the most stable on the most substituted carbon. A negative charge is the most stable on the least substituted carbon. Perhaps I should write that. Negative charge, most stable on least substituted carbon. And so because we're trying to have stability for a negative charge, that negative charge is going to be the most stable on a primary carbon and the least stable on a secondary carbon. And so the 1-pentene is going to be the major product because of the stability of the charge at the transition state, not the stability of the final product. Oh, ha ha ha. Carbanions versus carbocations. The most stable carbocation is the most substituted, but the least stable carbanion is the most substituted. So we know that positives and negatives are opposites, and this is just further evidence that positives and negatives are opposites. Leaving group effects on product distribution. Okay. Does the leaving group affect the product distribution? For iodide, bromine, and chloride, there is a small effect. on the leaving group substitution, or on the more stable product. But the more stable product for iodine, bromine, and chlorine is still going to be the major product. Only fluorine produces the less stable product as the major product. And you might associate this with the pKa. HI, HBr, and HCl are all strong acids, but HF is a weak acid. Okay, so relative reactivities of alkyl halides in an E2 reaction. So what is the alkyl halide preference for an E2 reaction? And that is that tertiary goes into elimination through E2 more quickly or more effectively than secondary and then primary. So for secondary and primary for secondary alkyl halides, we almost always usually make both substitution and elimination products for a secondary alkyl halide. Then for the primary alkyl halide, SN2 is going to be the favored over E2. So a primary alkyl halide will favor an SN2 substitution reaction and only a minor amount of elimination occurs. Okay. And we know that a tertiary alkyl halide cannot undergo an SN2 reaction. But the tertiary alkyl halide will have competition if an SN1 reaction is possible. So for tertiary alkyl halides, it may be that we form both the elimination product and the SN1 product. Next, we can talk about the E1 reaction. Oh, what time is it? Haha, time to go to lab.